Okay, good morning, everyone. Our project is about designing a real-time FIR bandpass filter using high-level synthesis on FPGA, targeting 10 megahertz signal sampled at 50 megahertz. We are group 9, and our group members are Nasser and Anas Jibril and Ali Muhammad. Uh, so, next slide. Uh, we'll go through three parts, the background and tools and for implementation, and finally the result and the trade-offs. Uh, okay. The problem was simple. 10 megahertz signal corrupted by noise that we need to recover in real time. We used an FIR bandpass filter because it's suitable and has a linear phase and maps well FPGA hardware. We had two hard requirements: SNR above 20 dB and throughput above 50. A regular CPU handle the SNR easily, but real time 50 is where you need on FPGA and FPGA. So next slide. Our flow was 5 steps: Python to design the filter, C++ to prepare it for HLS, Vitis HLS to generate the RTL, Vivado to implement it physically, and finally optimize version to meet our throughput target. The target chip was the Kintex UltraScale Plus, which has more than enough resources for our 127 tab filter. Now we'll move to Ali. Next slide.
Right, assalamu alaikum everyone. Assalamu alaikum, Bakr. Now we're going to move with part 2, which is our first task, which is Python. We started in Python. We designed a 127 tab bandpass filter from 9 to 11. Sampled at 50 megahertz. Nasser, go to the report, please, figure 2 and 3. Yeah, so as you can see here at figure 2, it shows the filtered signal cleanly recovering the sine wave, and figure 3 shows the frequency response flat in the passband, strong attenuation outside it. The SNR came at around 22 dB, which passes the requirement. So back to the slides, please. Slide 6. Yeah, so for the C++ part, we then rewrote the filter in C++ in a way that HLS tools can understand single sample at a time, no dynamic memory, bounded loops. SNR stayed at around 21.91 dB, matching the Python, or almost similar to the Python. Back to the report, please. Figure 4, yep. So as you can see here at figure 4, it confirms the match in the test bench output. Then we synthesized it with no optimization at all. And at figure 5, yep, at figure 5, it shows the baseline unit. I'm sorry, the baseline result, and an initiation interval of 33,000 cycles per sample. That gives us only about like 7,000 samples per second. We need 50 million, way too slow. Back to the slides, please. So at slide 7, you can see the optimization. So to fix that, we applied our things, loop vision to separate the shift multiply operations, complete array partitioning to make all 127 tabs accessible at once. So the loop unrolling to run all 127 multiplication in parallel, and pipelining with two equals, so we accept a new sample every clock cycle. Back to the report, please, figure 6. So as you can see here, figure 6 shows the result. It dropped from 33,000 to 1. So latency from 33,000 cycles down to 511. The SNR unchanged at 21.91. Back to the slides, please, slide 8. Yeah, so after full place and route in Vivado, back to the report, figures 7 to 10. Figure 9, sorry. Okay, so as you can see here, figure 9 shows timing met with 1.5 nanoseconds to spare on a 6 9 nanoseconds clock, giving us 223 megahertz with TI equal to 1. That means 223 throughput, which is 4.46 times the requirement. And figure 10 shows the figure 10, please. Yeah, and as you can see, figure 10 here shows the total power at around 2.783 watts. And now we're moving on with my teammate Anas.
Assalamu alaikum, everyone. Moving on. You can see in this table the full picture across all four implementations. The most important thing to notice first is that the SNR stay locked at that 21.91 dB from C++ all the way through to the final FPG. Every optimization we applied was purely about hardware scheduling. The filter math never changed. On throughput, the baseline gave us 7,000 samples per second. The optimization design gave us 223 million. That's roughly 32,000 times improvement just from restructuring the sample algorithm. On resources, LUTs grew 5.6 times, flip-flops 4.5 times, and DSP jumped 62 times from 10 to 623, and the power went from 0.662 watts to 2.783 watts, about 4.2 times. That's the real cost of going from sequential design to a fully parallel one. Next page, please. Okay, now let's talk about whether these costs were worth it. The throughput gain is about 56,000 times. The area cost is LUTs at 5.6 times, DSPs at 62 times. When you're looking at these ratios, it's very favorable trade. It's not like it's just the nature of FIR filters. Every output sample is just a dot product of fixed length vectors. There is no dependencies between outsample ones, the shift done, so you can parallelize almost without limits. The DSP number also makes sense when you check it against theory. Each step needs roughly 3 DSPs for the float point multiplier and 2 for the adder. So the 127 taps times 5 gives us the theoretical 635 DSPs. We've got 623 within 2% of that. The small difference is Vivado fusing a couple operations together during the place and route. Power is also worth discussing. We went from 0.662 to 2.783 watt, only 4.2 times growth despite 6 times increase in DSP count. The reason is that those extra resources are clocked at the same rate, and many of them are idle on any given cycle. The dominant power consumers are the DSPs at 0.64 watts, signal routing at 0.68 watts, and CLB logic at 0.61 watts. One thing to note, Vivado flagged the power estimate at low confidence because we didn't capture a switching activity file. For a more accurate number, you need to run a post-implementation simulation and feed the data back in. Next slide, please. Okay, to wrap up, both project requirements were fully met. SNR of 21.91 dB consistent from Python throughout C++, all the way to the physical FPGA and a throughput of 223 mega MSPS, giving us a 4.46 margin over the 50 MSPS target. The most impactful next step would be moving floating point to fixed arithmetic using AP to fixed right now. Each tab costs roughly 5 DSPS, because of the floating point hardware blocks. With fixed points, each tab uses about 1 DSP, so the count could theoretically drop from 623 down to around 127, which should also cut dynamic power significantly as long as we keep enough fraction bits. The 20 dB SNR requirement would still be met. Other feature directions including wrapping the filter in AXI4 stream interface for easy SoC integration and exploring the transposed form FIR architecture, which can shorten the critical path and make timing closure easier. Overall, this project showed the complete HLS-based FPGA data design flow in action from Python algorithm all the way to physical implementation, timing closed, power analysis design running at 223 megahertz on a real silicon. Thank you.